Oh, hey there again, old friend. Looks like you caught me drinking coffee again. I actually read a study that drinking coffee can help reduce the risk of Alzheimer's and dementia and what was I saying again? Well, regardless, we have a final coming up and we have a lot to do before it. Um, Now, I know you're probably really stressed, but you really shouldn't be, because if you pass, then you pass, but if you fail, then there's a silver lining. You and me get to hang out again next semester, hopefully in person. And I really like this quote here: what if my hard work pays off? It's a really good one to think about, because one day you'll graduate and I'll still be a student forever. Well, anyways, we really do have to get started on the final recitation. We have some new topics, such as the master's theorem, which is pretty much the easiest thing you'll learn this semester, but we're also going to be doing some old topics with some new and old problems. Now, this final recitation will be narrated and performed by my past self. So, without further ado, let's get started. And it will be going through the problems a little more quickly, so remember, you can always pause, rewind if you need to. All right, let's get started. We have one more recitation to go over, and that'll be this one. Today we'll be going over the master's theorem, which is really great because you don't have to think or anything like that. You just have to plug in a bunch of values following the rules that's given. We see some equations up on the board. We see that the master's theorem has three cases. One case where the recursive relation will have theta of n to the power of d. In the second case, we have big theta, n to the power of d times log of n. And in the third case, we have big theta, n to the power of log base b, a. So, really, that's very simple. We're always going to have a recursive relation given, and the format is this. Let's say that this is our first problem. We have t of n equal to t, and then plugging in n over 2, plus 1/2 n squared plus n. What is our a? Well, our a will be whatever we have multiplied by t of something, right? A times t of something. Now, of course, a here is 1 because we're multiplied by 1. Our b will be whatever's inside of the t function, n divided by b. So in this case, we have n divided by what? 2. So b is 2. Our d is not listed up here, but it belongs as the f of n. The d is the exponent of the most quickly growing component of that segment of the equation. Here we have 1/2 of n squared plus n. The most quickly growing exponent would be this 2 right up here. So d is 2. Now we do these equations. We get a is 1, we have some symbol, and we do b to the power of d. Is 1 less than 4? Is 1 equal to 4? Or is 1 greater than 4? Absolutely. So 1 is less than 4. So we are led to case number 1, where a is less than b to the power of d, because 1 is less than 4, given this equation. So our solution is case 1. Okay, and then big theta will be n to the power of 2. This next problem, a is going to be 2. B, we have a division by b within the recursive relation, so 2 again. And d, we have 10n to the power of 1, so d is 1. We have 2 is something, 2 to the power of 1. Now, of course, 2 is equal to 2, so we're led to case 2, which is big theta of n to the power of 1 log n. All right, our a here will be 4. Our b, we have an n divided by 3, so our b is 3. And then we trail off in this equation with 6n plus n. Now that's just 7n, and 7n has an exponent of 1. So d is 1. We get 4 is something 3 to the power of 1. Now, of course, 4 is greater than 3 to the power of 1, so we're led to case 3, which is big theta n to the power of log base 3 of 4. We have the set 1, 2, 3, 4, and we're given the following relation. Is it reflexive? Well, no, because it's missing the pair 1, 1. 1, 1 is not in the relation. Is it symmetric? Well, no as well. For example, we have 2, 4, but we do not have 4, 2. Is it anti-symmetric? No as well. We have 2, 3, and we have 3, 2, a case of symmetry. Then, is it transitive? Well, for this one, actually, yes. And we can list all the transitive pairings, and I'll do this below. It checks out, so it is transitive. All right. Reflexive? Yes. Symmetric? Yes. Antisymmetric? No. We have 2, 4, and 4, 2, both in our relationship. And transitive? Yes. Finally, C. Reflexive? No. Symmetric? Yes, because there are no symmetric pairs to test other than 2, 4. And 2, 4 checks out. It has a 4, 2. So therefore, yes, it is symmetric because all the cases which we must have symmetry on hold. Is it anti-symmetric? Well, for the same reason it's symmetric, it's not anti-symmetric. Is it transitive? No. We have 2, 4 and 4, 2, but we don't have 2, 2, so it's not transitive. How about this? A is taller than B. Is it reflexive? No, because no person is taller than themselves. It makes no sense to say A is taller than A. Is it symmetric? No as well. If A is taller than B, then B is shorter than A, not taller. Is it anti-symmetric? Yes, for the same reason that it's not symmetric, it is anti-symmetric. And transitivity, yes. Because if A is taller than B and B is taller than C, then certainly A is taller than C, right? Okay, A and B are born on the same day. It makes sense to say that A and A are born on the same day. So yes, it's reflexive. It is symmetric. It is transitive. It's not anti-symmetric for the same reason it is symmetric. A and B can both be born on the same day, and you can flip it to say that B and A were also born on the same day, which would hold true as well. So it is not anti-symmetric. X plus Y equals 0. It's not reflexive. Does it make sense to say that 1, 1 is 0? No. Is it symmetric? Yes. It is symmetric because addition is commutative. It's the same as saying y plus x is equal to 0, and that would hold true as well. Is it anti-symmetric? No. And we can give a counterexample. 2, -2 is in the relationship. That is to say, 2 plus -2 is equal to 0, but -2, 2, which is the reverse of that first pair, is also in the relationship. So there is some symmetry, therefore it's not anti-symmetric. And is it transitive? No as well. And we can use the same example here. This is in the relationship, this is also in the relationship, but 2, 2 is not in the relationship, therefore it's not transitive. X is equal to 2y. It is not reflexive. Plug in anything like 1, 1 and you'll see. Is it symmetric? Well, no as well. For example, 1, 1/2 is in the relationship, but 1/2, 1 is not in the relationship. Is it anti-symmetric? Well, yes as well. Any case of where the two sides of the pair don't match, the opposing side will not be in the relationship. So plug in any value for anti-symmetry and you'll see it is anti-symmetric. Is it transitive? No. Well, we have 2, 1, we have 1, 1/2, both in the relationship. But 2, 1/2 is not in the relationship, so therefore not transitive. Matrix now. Is it irreflexive? Well, not all of the diagonals are zeros, so no. Is it reflexive? No as well, because we have 3 diagonals which are not 1s. It is not reflexive. Is it symmetric? Yes, because it's mirrored across the diagonal. Is it anti-symmetric? Well, we can give many examples as to why it's not anti-symmetric. This one corresponds to a 1 on the other side of the diagonal, and so that's a case of symmetry. Therefore, no, it is not anti-symmetric. Is it transitive? Well, we can kind of eyeball it. We have this first column and this first row. There's a 1 in this spot, 2, 1, and there's a 1 in this spot, 1, 2. However, they intersect at a 0. So therefore, it is not transitive. 4b now, is it irreflexive? No, not a single diagonal is 0. Is it reflexive? Yes, all of the diagonals are 1s. Is it symmetric? Well, no. For example, this 1 corresponds to a 0 above. It's not mirrored on the diagonal, so it's not symmetric. Is it anti-symmetric? Well, this 1 corresponds to a 0, this 1 corresponds to a 0, this 1 corresponds to a 0, and finally, this 1 corresponds to a 0 as well. So it's flipped on the diagonal, it's reversed. Therefore, it is anti-symmetric. Is it transitive? No. We have 1, 2 and 4, 1, both in the relationship, but 4, 2 is not in the relationship. In other words, 4, 1, 1, 2 are both in the relationship, but their intersection is a 0, so it is not transitive. Warshaw's algorithm, we're given this relationship on this set. What does the original matrix look like? Well, we have 1, 2, so down 1 across 2. We have 2, 1, so down 2 across 1. We have 2, 3, down 2 across 3. We have 3, 4, so down 3 across 4, and 4, 1. The rest are zeros. All right, so let's perform. What does this look like after k equal to 1 loops? Again, we take the first column and the first row, and we look at all the intersections, and we add new edges or new relationships to fit our new transitive relation. We're intersecting at the 0, so this becomes a 1. This 0 also becomes a 1, and that's it for the first loop. How about loop 2? We look at the second column and the second row. These two 1s intersect at this 0, so it becomes a 1. These 1s intersect at this 0, so it becomes a 1. This 0 becomes a 1 as well. Loop 3 now. Column 3, row 3. We get that this becomes a 1, and so do these. Finally, on our last loop, we check the fourth column, the fourth row. All 3 of these remaining zeros become 1s, and our final solution is a matrix filled with every place filled with a 1. Draw a diagram given this set on the relationship of divisibility. So we begin with 2. 2 is a node on its own. 3 does not divide anything currently in our hash diagram, so it goes on its own as well. Next, 5, 10. Now, 2 divides 10 and 5 divides 10, so we draw relationships from 2 to 10 and from 10 to 5. Then we have 11. 11's on its own. 15. 5 divides 15. 3 divides 15. And finally, 25. 5 divides 25, and that's all that divides 25. So let's create a hash diagram for this posit and answer the following questions. 2 is on its own. 4 is divisible by 2. 6 is also divisible by 2. 9 is on its own. 12 is divisible by 4 and 6. 18 is divisible by 6 and 9. 27 is divisible only by 9. 36 is divisible by 18 and 12. 48 and 60 are both only divisible by the 12. Now, of course, they're also divisible by everything below 12, but at the highest level, they are both divisible by 12, so we only add an edge from 60 to 12 and from 48 to 12. Similarly, 72 is divisible by 36 at the highest level. So we have this hash diagram. Are there any maximal elements? Well, our maximal elements would be the endpoints at the top, which would be 27, 48, 60, 72. Minimal elements would be 2 and 9. There is no greatest element and no least element. Upper bounds of 2, 9, well, 2, 9 have the upper bounds of 18, 36, and 72, because we can get to 18, 36, and 72 by going up from 2 and up at 9. So, in other words, 18 is divisible by 2 and 9. Similarly, 36 is divisible by 2 and 9, and same with 72. 18, 36, 72. The least upper bound would be just the least of those, which is 18. Any lower bound of 60, 72? 60 and 72, well, we go down from 72, down from 36 and get to 12. At 60, we go down one time and get to 12 as well. So they join at 12, therefore, 12 would be one lower bound, but so would be 4, 6, and 2. The greatest of these would just be the highest one, which is 12. We have the same hash diagram as in a previous recitation, and we want to find a compatible total order. Let's find one that's different from the one we found last time. This time, let's first remove the minimal element, B. Now we have 3 options to choose from, A, E, or C. Let's remove E next. Then we have 2 options, A or C. H is not a minimal element because H has a relationship with A through D. So instead, we remove C. After C, let's go for A. After A, we have 2 options, D or F. Let's go for F. From there, we can go for G or D. We're going to go for D. From there, H. From there, let's go for G. So I. We remove K, J, M, and finally L to create the following compatible total ordering. Okay, let's write an algorithm. Our input is an array from, we'll call it A, goes from 1 to n, number of elements within that array, and then our output is the largest difference of subsequent elements within that array. So we begin, let's say max is currently negative infinity. It's a very low number because we haven't found it yet. Then we make a for loop. Let's go from I. Let's go I from 1, 2, and minus 1. And we do the following. We have an if statement. If A of I plus 1 minus A of I, that is, we're checking the next element, the subsequent element in the array from our current position I, with the current element at the position I. And if this is greater than max, at the first loop it certainly will be, with max being negative infinity, Then we do the following. Max is updated. It becomes equal to a of I plus 1 minus a of I. Max is now the difference between one element and the next element in the sequence. We end our if statement, and we end our for loop. We return max. And also, our algorithm will run in big O of n. That's because within our for loop, we iterate from I to n one by one. So we're going to have a growth rate of n number of comparisons. That will be our growth rate of this function. Therefore, big O is n. Our input is an array, and again, our output now is the location of the last smallest integer within A. So we begin by setting a minimum value. Let's say that this is equal to positive infinity. Our location is equal to 0. That is, it exists at the 0th place within our array to begin with. So from there, we make a for loop. I is going to iterate from 1 to n. And we do the following. If a of I is less than or equal to the current minimum value, then we update min. Min becomes a of I, and the location of this minimum value is simply I within the array. Okay, we end our if, we end our for loop, and we return simply the location, which we called LOC, lock the location at that place within the array. This will run at a time complexity, the worst time complexity, of n, because we have one for loop which iterates I to n, and on each iteration we're increasing I by 1, and it's all about the rate at which we grow this function. The number of comparisons grows based on n. So you will have n number of iterations with this for loop, and big O becomes n. Let's give a big O estimate. We have the following: 5x squared plus 16. Now, when x is greater than 4, we have the following. We have that 5x squared plus 16 is less than or equal to 5x squared plus x squared. We increase the growth rate of one of the elements within 5x squared plus 16, to 16, to match the growth rate of 5x squared, so we essentially turn the 16 into x squared. And obviously this holds true because x squared grows more quickly than 16, that being a constant. So we know that this holds true when x is greater than 4. Now, this is also true that we can simply say 6x squared, we add them together and get 6x squared, which is greater than or equal to 5x squared plus 16. From there, we see that k is equal to 4 and c is equal to 6 at big O of x squared. Our 4 comes from x being greater than 4, that is when this equation and this equation intersect if we were to graph them, and the 6 comes from the factor we multiply by the x squared. So we have big O of x squared in the end as our big O estimate. X squared plus 10x. So when x is greater than 10, we know that the following holds true. X squared plus 10x is less than or equal to x squared plus x squared. We simply increase the growth rate of one of these elements, 10x, to become x squared, and we know this holds true. So x squared plus x squared is equal to the following, 2x squared. So our big O would be x squared when c is equal to 2, coming from the factor we multiply by the x squared here, and k is equal to 10, because it holds true when we have at least 10 data input into the algorithm. Okay, so part 4 now. Show x log base 2x is big O x squared. We could probably use the definitional method again. We see that x log base 2x is less than x for x greater than 0. Therefore, x log base 2x is less than x times x. This x remains the same. This x matches up with this x here on the right. But log base 2x, we increase the growth rate to match the x. So we convert the log base 2x into an x. We have that this following expression is less than x times x. Again, using this definitional method that we've been using for the previous problems. Now, this is just x squared. Therefore, k is equal to 0, c is equal to 1, and big O is x squared. The c equal to 1 comes from the fact that x squared times 1 is what we get here at the end. And k equal to 0 is just that the point where x log base 2x intersects with x squared. That being that they intersect at the 0th place if you were to graph them. Maybe this is x squared, and this is x log x, and they would intersect here at the very beginning. A few more big O estimate problems. 2x squared plus x to the power of 3 log x. Well, let's use the definitional method. When x is greater than 1, we have the following. 2x squared plus x to the power of 3 log of x is less than or equal to 2x to the power of 4 plus x to the power of 4. We got this by converting log of x just to an x, which gives us x to the power of 4. This is converted to this x to the power of 4. 2x squared, the growth rate of 2x squared is increased to try to match the most quickly growing component of the expression, that being x to the power of 4. So, 2x squared, the exponent is increased to match the exponent here. Okay, so we know that this holds true. Therefore, when k is equal to 1, coming from here, and c is equal to 3, coming from 2x to the power of 4 plus x to the power of 4 being 3 times x to the power of 4, that's where c came from, we have that 2x squared plus x to the power of 3 log of x is big O x to the power of 4. All right, so we have a fraction here, x to the power of 4 plus x squared plus 1 over x to the power of 4 plus 1. As x increases to a very large number, this fraction essentially just becomes very close to 1, right? So let's say when x is greater than 1, we have the following. F of x, which is just this expression here because I don't want to rewrite it here, is less than or equal to 3x to the power of 4 all over x to the power of 4. We drop the constants, and we drop the constant here on the right, and on the left, we increase the growth rate of x squared to make it x to the power of 4. We increase the growth rate of 1 and make it x to the power of 4 as well. So x to the power of 4 plus x to the power of 4 plus x to the power of 4 gives us 3 times x to the power of 4. This expression here is equal to 3. We cross out the x to the power of 4's and we're left with a 3 right here. 3, or in other words, 3 times x to the power of 0. Therefore, when k is 1 coming from here, c is 3 coming from here, then we get big O of x to the power of 0, or a big O of 1. It is a constant worst time complexity algorithm. Now we do a big omega estimate of the following. X to the power of 3 plus 22x squared plus 99. Well, for x greater than 1, we have x to the power of 3 plus 22x squared plus 99 is greater than or equal to x to the power of 3, right? Because x to the power of 3 is the most quickly growing component within this function. Then, well, we're done. Therefore, k equals 1, c equals 1, and f of x is omega x to the power 3. So now show 3x squared plus 8x log of x is big theta x squared. Now big theta is a type bound, so it's also big O of x squared, and this expression is also big omega of x squared. So we're going to have to do two problems, actually. First, when x is greater than 0, 3x squared plus 8x log of x is less than or equal to 3x squared plus 8x squared, right? We change this log of x and turn it into an x. And then we get 8x times x, so it's 8x squared. This is less than or equal to 11x squared, right? Because you just add them together and get 11x squared. So therefore, when k is 0, c is 11, the following expression is big O x squared. Now we have to show that it's also big omega x squared. So when x is greater than 0, 3x squared plus 8x log of x is less than or equal to 3x squared. It's just the most quickly growing component within this expression. And then, well, we're done. K is equal to 0, c is equal to 3, which we get right here, multiplying the factor of x squared. And we have that this expression is big omega of x squared. So, because we have that it's big O x squared and big omega x squared, we have that it's big theta x squared. So, it holds to be true. We use the limit method with the following rule. We have f of x and g of x. So we get the limit as x goes to infinity of log base 2x all over log base 3x. This is just equal to the limit of x to infinity of log base 2x all over 2 times log base 2x all over log base 2 of 3. So this log base 3x becomes 2 times log base 2x all over log base 2, 3. All right, so from there, this is just equal to the limit as x goes to infinity, log base 2, 3 all over 2. And if we did the math here, we would get that this is equal to 0.7924, which would be our solution. And how did I get this? Well, you're just gonna have to trust me here. How are you enjoying the recitation video so far? Well, up next is we're going to be doing induction, and I thought it'd be nice to review what exactly induction is. So we can imagine induction kind of like a ladder. Now, a proof by induction can be a little daunting, so I thought we would go over what exactly a proof by induction is doing, right? So we can imagine a proof by induction as kind of like a ladder, right? So we have a first rung, and it goes all the way up to infinity. Let's just say, in this case, it's P of 1, right? The base case exists. A first rung exists on this ladder. Now we have a total number of n rungs. Now n could be as high as we want, but we're just assuming there are n total number of rungs. Now our inductive hypothesis would be to assume that some rung within that n number of rungs exists. So let's assume that some rung, well, look at it, this one here, exists. And we'll call it rung K. So rung K is assumed to exist. Our inductive step would be to then prove that the rung above it also exists. And if we can show this, then we can pick out any rung at any point and say that's rung K. And because rung K exists, this also means the rung above it exists. And so that ladder will go on forever. So we assume P of K exists, and we want to show that P of K plus 1 also exists. And again, this would show that the ladder goes on forever, which is just a proof by induction. Prove that the sum of I to n of I squared is equal to the following formula for all n greater than or equal to 1, and we have to use induction. So this one's very complicated, but I will go one step at a time. we have the base case. In other words, when n is equal to 1, we have the following. The sum of I equal to 1 all the way to 1, I squared, is equal to the following. 1 times 1 plus 1, 2 times 1 plus 1, all over 6. Now, of course, this simplifies down to 1 is equal to 1, which is true. So, because it's true, the base case holds. Next, we have our inductive hypothesis. In other words, our assumption. So, we plug in k for n. We have the sum of I to 1 iterating through to k, and I squared, and we assume this holds true. k plus 1, 2k plus 1, all over 6. All we simply did was take this formula here and replace all n's with k. Next, we have our inductive conclusion that we need to prove. So we set it up. We have the sum of I equal to 1 to k plus 1 of I squared is equal to we simply take the k plus 1, turn it into a k, and then add what we would have added with that final loop here at the tail end. This is simply simplification. We know that the sum of I equal to 1 iterating to k of I squared is what we've assumed it to be. We assumed it to be this expression here. So we use the inductive hypothesis by plugging it in there. We are going to put everything on a common denominator. To do this, we multiply this segment by 6 and divide it by 6, so nothing changes. From there, we can simplify. We simply put it all under one common denominator. So we use the inductive hypothesis, we add a common denominator, and we simplify it all in one step. From there, let's factor out the k plus 1. We get, okay, so now we simplify. So we have k plus 1 times 2k squared plus 7k plus 1 all over 6. We got this by simplifying. From there, let's factor out, let's take this polynomial here, 2k squared plus 7k plus 1, and convert it into something more simple. So we factor out this final step, and we see we have an integer times some integer divided by 6. Now you'll notice that this expression here, n times n plus 1 times n 2n plus 1 over 6, matches this expression below if we replace all of the n's with k plus 1. So, because it holds true that the sum of I equal to 1 all the way through to k plus 1 of I squared is equal to what we were trying to prove, then it must hold true. This expression holds true. So my video recording died as I was almost done with the problem, so I didn't want to rewrite everything, but let's explain what we have so far. Question 10 is 1 squared plus 3 squared plus 5 squared all the way up through the definition of an odd integer. 2n plus 1 squared is equal to the following expression whenever n is a non-negative integer. So we want to prove this by induction. Our base case is the first non-negative integer, that is, n is equal to 0. So we simply plug n in for 0. We get 2 times 0 plus 1 squared, which is 1. And we get 0 plus 1 times 0 plus 1 times 0 plus 3 over 3, which is also 1. Therefore, the base case holds. Our inductive hypothesis is simple. We just replace all of the n's in what we're trying to prove with k, and we assume it to be true. Now, we want to have an inductive conclusion. The inductive conclusion is going to be replacing all of the k's with k plus 1. So we have 1 squared plus 3 squared, all the way up through 2 times k plus 1 squared. That's equal to k plus 1 plus 1, 2 times k plus 1 plus 1, 2 times k plus 1 plus 3 all over 3. We want to show that this is true. Let's begin with this side of the expression and show that it's equal to this over here. So as we know, this is a increasing sequence, and we're adding whatever is before. It's always going to have something squared, and the base is increasing incrementally by every odd value. So it's 1 squared, 3 squared, 5 squared, 7 squared. We see that this is equal to 2k plus 3 squared. What would be right before this within the sequence? Right before it would be 2k plus 1 squared. So 2k plus 1 squared is right here within our sequence, right before this value here. But as we know, everything in the sequence prior to this last element, 2 times k plus 1 squared, has already been assumed to be something else. It matches here, which I will do in green so you can see. This part of the expression matches the beginning sequence of this expression. And we already know what that's equal to, so let's just plug in what we know by our inductive hypothesis. We get the following. Nothing happened to the 2 times k plus 1 squared. That remains the same. And we're trying to show that this part of the expression is equal to this. All right, so let's do what we did before. Let's try to match the denominators. Multiply this by 3 and divide by 3. Then it's easy. We can just put it all under one common denominator. This is all equal to all divisible by 3. From here, let's do some algebra and simplify. Now, we do the very complicated algebra here. We multiply all these together. We add it to simplification of this form as well. We will get 2k plus 3 times k plus 2 times 2k plus 5 all over 3. You can do it yourself, but just trust me that this expression is equal to this up here. From there, let's rewrite it one more time. We get, and we see, that this is equal to what we have up here, right? So if we replace all these 1 plus 1s with 2s, we replace this part of the expression with 2k plus 3, right? That's just how the algebra works out. And we know that 2 times k plus 1 plus 3 is also 2k plus 5. We've shown that this expression here, 1 squared plus 3 squared all the way up through 2 times k plus 1 squared, is equal to this expression. And this expression matches what we were trying to prove. Therefore, by induction, our original statement is proven. Another proof by induction. 3 plus 3 times 5 plus 3 times 5 squared times all the way up through 3 times 5 to the power of n is equal to 3 times 5 to the power of n plus 1 minus 1 over 4, when n is a non-negative integer. So our base case is 0, the first non-negative integer. Of simply this expression, replacing n with 0, we get this here, and of course, this is equal to, or it matches the following. 3 is equal to 3, which holds true. Therefore, the base case is proven. For our inductive hypothesis, we replace n with k, and we get that this is our assumption. We assume this to be true. All right, so we want to prove that this increasing sequence is equal to 3 times 5 to the power of k plus 1 minus 1 over 4. Just replacing all of the n's with k plus 1. We know that this is the last sequence or the last element in the sequence. Right before it, we have 3 times 5 to the power of k. By our inductive hypothesis, these segments match. So we replace the segment with the following. Now it's more simple. We have to show that this expression equals the right-hand side of this equal sign. So let's do the same thing we did before. We match the common denominator, and then we combine them so it's all one expression. From there, let's do the algebra. Let's simplify. All right, we get the following. let's simplify a little further. We're going to want the algebra here to get it to match up with what we have on the right. Here's our next step. Let's go one more step further. We get 3 times 5 to the power of k plus 1 minus 1 over 4. Does this match up with this up here? Absolutely. So we have proven our inductive conclusion using our inductive hypothesis, which proves that the original statement holds true. The final problem. Bacteria triples every hour. Okay, so it's a recurrence type problem. Set up a recurrence relation. Okay, so let's begin by saying that B of n is how many bacteria we have at the nth hour. We know it's based on the previous hour, so let's just say B of n is equal to B of n minus 1 times 3. Solution to A. Part B, if 100 bacteria begin in a colony, how many bacteria are there in 10 hours? Well, our initial condition is 100, and we have that n is equal to 10. We know B of n is equal to 3 of B of n minus 1. We replace B of n minus 1 with whatever B of n minus 1 might be. We expand it in a sense. B of n minus 1 will be this expression with all n's replaced with n minus 1. This is equal to 3 times B of n minus 2. So let's expand B of n minus 1 with this expression here. We get 3 squared B of n minus 2. The next step will give us B to the power of 3, B of n minus 3. We do this up to n number of iterations. We get 3 to the power of n times B of n minus n. Now we know this is 0, so we get 3 to the power of n times B of 0. Simply replace n with 10 and replace B of 0 with 100. And what do we get? Well, we get 5,904,900, which is how many bacteria we will have in our colony after 10 hours. Okay, so that ends the final recitation of the semester. So if you made it through all of them, I applaud you, and I hope you do very well on the final.